I was sick on Saturday, so I've been here much. That's okay. Please do like the live. Andrew and Harper, if you could like the live, that would be amazing. Thank you so much. So, in 1905, we got all these great contributions from Einstein. And around that time and before, of course, we saw a lot of developments in E&M, electricity and magnetism theories, and then special theory of relativity gave us the even more updated theory for light. But then on the other hand, we also got the particle nature of light with the photoelectric effect. So this whole wave particle duality of light also led some people, influenced them to think about the wave particle nature of matter as well. So we talked about quantum mechanics and how it kind of developed in parallel, along with sort of the more classical type of physics or the relativity type of physics, because of course Einstein worked on special theory of relativity and then also worked on general theory of relativity. And along with all of this work, developed something quite interesting, bizarre, very different, very unique, and very new, which is, of course, quantum mechanics. And we got the wave nature of matter. So this whole development was extremely interesting, extremely amazing, and extremely intriguing. And we have covered the history of this in detail in those lives that I mentioned from October and November of last year. So if you're interested, you should definitely tune into those and listen to those. And I think you'd find them to be very entertaining because we got into all of the nitty-gritty and we had very good discussions. Now, because quantum mechanics was bizarre, there were people who didn't really like it. In fact, there were people who had contributed to quantum mechanics who didn't like it, such as Schrödinger. He wrote down the wave equation for a particle, and later on, people realized that this is actually a probabilistic way of writing down the wave equation of a particle, and you actually get a probabilistic answer from that. So classical mechanics is deterministic. Everything that people kind of knew so far was deterministic. It's like when you write down the position of something as a function of time, it's predictive, you know it. I can tell you where the moon will be in like 20 years, that type of thing. People were used to, like classical mechanics supported the old sciences. Astronomy is really old, right? We've been doing astronomy for forever. And classical mechanics gave us a way to understand and postulate, encapsulate, describe, explain astronomy, astrophysics, all those types of things in such a good way, in such a deterministic way. All the laws, the Newtonian mechanics, the Kepler laws, all of that is deterministic. It is, can I see your cat? Yes, in a minute I will show you Baji. He's right here, but I don't want to move the camera right now. It was very good at giving people answers to things in a sort of, we get it, we understand it, we can predict it kind of way. And all those laws, the planetary motion laws, the, in general motion laws, everything it was very deterministic. So when we started to work on quantum mechanics and we developed quantum mechanics and we said that now when you write down the equation for a particle, its position as a function of time, you can't actually know it deterministically. You can only come up with a probabilistic answer for that. And uncertainty is a fundamental aspect of nature. It's not that we're making errors in measurement. At those small scales in quantum mechanics, you have uncertainty and things will be probabilistic. So even some of the people who contributed to quantum mechanics actually were very uncomfortable with it, and they were not very happy with the fact that this was so different and so bizarre. And of course, there were some actual bizarre outcomes as well. And quantum mechanics could have been dead had it not been for